Swayam Prabha. Digital India. Educated India.
Good morning. Today we are going to start this techniques of polymer manufacture. You know, polymer products are made from polymer raw materials. Polymer raw materials I mean polymer raw materials I mean polymer in the form of granules, flakes, powder, beads, solution, suspension. So, the polymers raw polymeric materials are available in these forms. These are blended with functional additives to manufacture polymer products. These polymer raw materials along with the functional additives, they are mixed together to form a polymer compound. Then that polymer compound subjected to various fabrication techniques, processing and fabrication techniques to get the polymer products. We shall discuss that part later. Today we are going to discuss how these polymer raw materials, particularly this basic polymer in the form of granules, flakes, powders, beads, solution, suspension, they are made in industrial or commercial scale. Now, there are techniques of polymer manufacture. Polymer can be manufactured by homogeneous system as well as heterogeneous system. Sometimes this manufacturing system may be initially homogeneous, but afterwards in later stage it becomes heterogeneous. We shall discuss those things. And out of these homogeneous and heterogeneous system, in general we can say there are techniques like bulk polymerization, solution polymerization, suspension polymerization and emulsion polymerization. Okay. You know there are two major different principles of polymer synthesis. Condensation polymers, condensation principle and addition principle. Not both of these principles can be applied for making or for manufacturing polymer using this bulk technique or solution technique, suspension or emulsion technique. It depends on the characteristics of the polymerization reactions. You have seen that condensation polymers are synthesized using monomers and it occurs in various intermediate steps, and this polymerization is not highly exothermic, it is less exothermic polymerization system, whereas addition chain polymerization is highly exothermic polymerization. Why I am telling this thing? Because in industrial manufacture huge batch is involved, that means huge quantity of monomers and other ingredients, those are charged to the reactor for manufacture of the polymer. You have seen in a simple laboratory synthesis of a chemical compound, you need a container. In that container you take the monomer or the reactants, you add the ingredients, provide sufficient conditions of environment, say either inert environment or in presence of air. Then you have to raise the temperature of the reaction vessel to the level of the activation energy, so that reaction starts and continues. After that, simultaneously it needs stirring, agitation of the mass, and that is a very small quantity, maybe 50 grams or 50 milliliter or 100 grams or 100 milliliter, be it in liquid form or in solid form. There stirring is very easy. Now, in the laboratory synthesis of polymer, you can use a simple magnetic stirrer. I think you have seen what is magnetic stirrer. It is nothing but a plate below which there is a motor with a fitted with a magnet, and on the top of the plate if you place your vessel, and inside the vessel if you keep a magnetic bar means a iron bar coated with Teflon or other inert polymer. Then if you rotate the magnet below the plate of the magnetic stirrer, so that will rotate the inside magnetic bar inside the polymerization vessel or reaction vessel. So, this way you can stir, or there are available mechanical stirrers. Say if the batch size is bigger than that, which cannot be controlled or accommodated by that magnetic stirrer, then we need a mechanical stirrer, laboratory scale mechanical stirrer. Okay. That mechanical stirrer is fitted with a motor, and on one side the shaft of the stirrer is fitted with a motor, and on the other end there is a blade is fitted, blade of different design and shape that is fitted there, and it rotates by electrical operation, and we can get the stirring. In industrial scale, that stirrer is a huge stirrer. Then control of temperature, in case of laboratory synthesis, what you do? You can use a heating mantle. Have you seen heating mantle? It is a container. It is a container of different volume, where you can place your round bottom flask of say 100 milliliter to 1 liter or more, and within that mantle the electrical heater elements are there. So, you can change the temperature with the help of a temperature controller. So, this way you can supply the heat to the reaction vessel and carry out the polymerization or any other reaction. In case of industrial polymerization, what happens? You have to supply the heat either by electrically or by hot gas or by hot oil, and here the heat transfer surface is very much important. Heat transfer surface means you have to supply the heat to the container or the reactor, so that the entire mass is homogeneously heated. That means, the temperature becomes uniform within the reactor. So, that simple heating mantle type heating system is not there. So, there may be heating coil or other systems which can supply the heat to the polymerization vessel. It may look like this, say so this may be a simple sketch of a reactor. Now, this is a huge stirrer which is fitted with the motor. Then that may be a vent. This may be connected to a condenser, etc. So and so, and inside there can be baffle. Many things. If you look at some typical reactor design and other things, you can see all these things. So, within this reactor, monomer and other things, they are charged. Then heat is supplied either by electrical heating, say you can consider this as electrical heating coil, or it can be a tube. It can be a tube through which hot oil or hot gas which is passed through this coil, and it hits the actually I am little wrong, I should show this coil from there. So, actually it remains immersed in this liquid inside this kettle. So, heat is supplied. Now, here is the heat transfer surface, the surface of this tube provides you the heat transfer surface. Not only that, there may be jacketed heating by outside jacket. Again, the thermal conductivity of the material of the reactor is plays an important role there. From outside jacketed heating I have not shown here. So, that is also used. Not only that, the outside jacket can also be used for cooling system. Not only that, this same heating system can be used as cooling system also. So, if you pass some fluid through this hot fluid, so this tube sometimes you can pass also cold fluid. So, this way it can keep the temperature controlled inside the reactor. Now, we are going to discuss this bulk polymerization, say batch type bulk polymerization, continuous type. Now, batch type, you do not know what is batch type. Now, this polymerizations or chemical manufacture, they both these can be carried out by batch process or continuous process. There are advantages of both these techniques, again with serious disadvantages too. I mean that in case of batch process, the productivity is less, whereas in continuous process the productivity may be high. In order to get higher productivity, higher amount of polymer manufacture in short period of time, one should go through continuous process. Whereas in a batch process, the reactor I have shown, say that is a batch reactor, where you have to give a charge, say one time charge of monomer and other ingredients, then supply these sufficient conditions and polymerization starts and continues, and after the polymerization is over, that means after suitable level of conversion, say 60% or 70% conversion, you have to stop the polymerization, then you have to remove the mass from the reactor, and after removing the mass from the reactor, you have to isolate the unreacted monomer and other ingredients present over there to get the polymer. Okay. So, that that actually needs more time. So, the productivity, the total quantity of polymer manufactured per day will be less, whereas in a continuous process, if these monomers are continuously fed to the reactor in one side, and from the other side if the product is collected, then there will be higher productivity. But the problem is, in continuous process one cannot go to higher conversion. Higher conversion is not possible. Higher conversion, I mean you can get high molecular weight product, but the conversion may be 20%, 30%, because there are problems like viscosity and other things, handling of this entire mass. So, it is carried out up to lower conversion, and then there needs a provision for recycling, isolation, separation, isolation, purification of the unreacted ingredients, and those isolated, separated and purified unreacted ingredients, again they need to be recycled to the initial or the recycled to the reactor. Again in batch reactor there may be only one vessel which is used for polymer manufacture. In continuous process, a series of reactors in a battery, like say battery of 10 reactors may be connected in series, okay, and in each reactor the conversion may be less. So, when it comes out of the last reactor, you can find a higher conversion, and then it needs some units of separation, isolation, purification, etc. From there again you have to recycle the unreacted ingredients to the first reactor, and it goes on continuously. So, from one side you are feeding the monomer and ingredients, from the other side you can get the polymer. Here actually in polymer manufacture there are certain unit operations unit operations, various unit operations are involved. Probably you have heard these two words, unit operations. These unit operations are the subject matter of chemical engineering. Say unit operation may be mass transfer, heat transfer, separation, purification, distillation, size separation, your size reduction like crushing, grinding, all these things. Purification may be distillation, stripping, etc. So, those unit operations, if time is available, I shall cover in one lecture later, not today.
Sir, why is this condensation process non-exhaust?
Coming. So, this all these polymer manufacturers, they involve unit operations for getting high productivity of this polymer, higher quality of the polymers, desirable properties of the polymers. Now, you have asked a question like why condensation polymers are less exothermic. You think of the polymer synthesis by condensation process, where it occurs in various steps. It is a slow process. It is a slow process and very slow process, and there may not be very large number of sites where these slow steps are occurring in one time, because you know this polymerization reactions depends on the collision factor. I told you out of 10 to the power 13 collision, only one collision may be effective for carrying out this reaction or polymerization. So, this condensation polymerization is less exothermic, whereas in case of addition chain polymerization, depending on the initiator free radicals availability, there may be large number of polymer chains can start from the beginning, and at the same time, since this kinetics is very fast polymerization occurs. So, all on a sudden there may be huge quantity of heat generation. So, that is why we say that addition chain polymerization is highly exothermic. So, addition chain polymerization is difficult to manage in industrial polymerization. That is why people go for tubular reactor. There are various designs of reactor. Say people use tubular reactor, narrow tube is a reactor, narrow tube in the form of your spiral, that is a polymerization reactor. From one end of the tube monomers are introduced, and from the other end polymers are collected. So, that helps you higher heat transfer area. Say in a gas phase polymerization, polyethylene manufacture, polypropylene manufacturing, gas phase polymerization, it provides higher heat transfer area. So, since it provides higher heat transfer area, so if that surface is covered with coolant, then exothermic heat generated in the polymerization reactor can be easily removed. Now, let us see what is bulk polymerization. Bulk polymerization is a technique mostly used for condensation polymers. Bulk polymerization technique is mostly used for condensation polymer. and in few cases of addition polymers. Examples may be polyester, polyamides, nylons, etc. And in case of addition chain polymers, say polystyrene, PMMA, what is bulk polymerization? It is a it is a heterogeneous system. Bulk polymerization falls under the category of homogeneous polymerization system. Homogeneous polymerization system. Bulk polymerization involves only monomer and catalyst or initiator. Depending on the nature of polymerization. In case of condensation polymerization, we use catalyst. In case of addition chain polymerization, we use initiator. Okay. And this bulk polymerization is homogeneous system. And we get purest form of polymer. Very high, if we need very high purity polymer, then we should go through this bulk polymerization technique, because after the polymerization, what will be the composition? Polymer plus catalyst or initiator residue. In case of addition chain polymer, there may not be any initiator residue in bulk polymerization, because if all the initiator molecules decompose, that will add to the polymer chain. And if we can allow sufficient time and condition, then entire monomer can be converted to polymer. So, in the product, here the raw polymeric product will be obtained only, that is only a polymer, no initiator residue, no other impurities. In case of condensation polymerization, you know, there is some byproduct which is eliminated, and that is removed from the polymerization system. So, that is also not present as impurity. Not only that, catalyst which is used for this condensation polymerization, that is very small quantity. So, if that is not considered as impurity in the polymer mass, so the product obtained from bulk polymerization does not require any purification step. So, bulk polymerization technique does not require any purification step, or it does not require any isolation or separation of the polymer from the monomer and other impurities etc. But there may be a problem. In case of condensation polymerization, it involves very high temperature. When I will show you this with the help of certain flow diagram, synthesis of polyester, manufacture of polyester or nylon, you will see that it involves very high temperature, because these intermediates, the melting points of the intermediates are very high. Until and unless this is not kept in a fluid stage, fluid phase, polymerization reaction cannot continue. Then it will be heterogeneous. The polymer will remain solid, dispersed in the intermediate phase in case of condensation polymerization. In that case, one cannot achieve very high molecular weight product. So, in order to avoid that, both the monomer, intermediates as well as the polymer of high molecular weight or higher molecular weight or higher sized polymer molecules all remain in molten condition. So, to keep them in the molten condition, the polymerization should be carried out at high temperature, because as the molecular size increases, the melting temperature increases. You have seen, isn't it, with that curve schematic diagram I showed you in earlier class, that if the molecular size increases, the melting temperature also increases. For that reason, condensation polymerization needs very high temperature for getting higher molecular weight product. Now, in case of addition chain polymerization, there are a lot of problems in a huge reactor. As it is highly exothermic, what happens? This polymer during its growth, huge quantity of heat is generated. It needs efficient stirring for heat transfer to cooling surface. Again, this polymer, addition chain polymers, which is formed, that remains soluble in the monomer phase, because it is a homogeneous system from initial starting point to the final polymerization step. So, polymer remains dissolved in the monomer. So, in this case what happens? Viscosity of the it becomes very high, becomes very highly viscous with the increase in conversion. Say 10% monomer converted to polymer, 90% remains as monomer. So, gradually the composition changes from monomer to polymer or monomer. Say suppose here if the 70% conversion is there, there will be 70% polymer and 30% monomer. So, 70% polymer remains dissolved in 30% monomer. So, it gives a very high viscous system. With this, at this high viscosity, it becomes very difficult to control the temperature of polymerization, because if the heat transfer system is not that efficient, there may be some hot spot generation. And this hot spot generated, that leads to auto acceleration. Or gel effect, and that can lead to Ranavi reaction, means it can lead to explosion and many other things. The entire batch will be destroyed. So, to avoid all these things, normally in case of addition chain polymerization, if it is done in the bulk by bulk technique, it is carried out, it is actually stopped at lower conversion, say 50%, 60% like that. Okay. That means, such type of polymerization can be carried out in 2 steps. You will see that here you see the direct casting of products. What does it mean? In order to avoid that high viscosity increase in a big reactor, so a pre-polymer of lower conversion is made, and that pre-polymer is used for direct fabrication of product. You think of Perspex sheet, PMMA sheet. Or plexiglass, plexiglass, these are trade names of this PMMA. How this is done? Now, first a pre-polymer, say up to 30% conversion or 40% conversion is made, which is a viscous solution. Then you can have a sheet mold, sheet die. It may be 1 centimeter thick sheet, 6 millimeter thick sheet, 5 millimeters thick sheet, or 20 millimeter thick sheet, like that. So, that is a sheet mold. That means, a mold, rectangular mold having a cavity, rectangular cavity inside. Now, this pre-polymer is poured into that cavity, and rest of the polymerization or conversion, say 70% conversion is carried out there. There you see only in that big sheet mold, this one dimension is narrow, 6 millimeter, 5 millimeter, 10 millimeter or 20 millimeter, where heat transfer can be easily controlled. One can have better heat transfer. So, this pre-polymer can be directly used for casting a polymer sheet. Say you have seen this scales, set square, etc. These are directly cast product from a pre-polymer of polymethyl methacrylate, where 30% or 40% conversion is carried out in the first step. In the second step, that is poured into that mold and directly it is cast. Okay.
So, by 30% conversion, you mean that 30% of the individual process is over, or 30% of the polymer is formed?
30% monomer is converted to 30% polymer. Say if you take 100 gram polymer or 100 kg monomer, 100 gram monomer or 100 kg monomer, if 30 kg of that entire monomer is converted to polymer, we say it is 30% conversion. Do you understand? That means 70% monomer remains unreacted. In that 70% monomer, this 30% polymer remains dissolved. like a viscous solution. Is it clear now? Okay. That is 30% conversion. 30% conversion means 30 gram of the initial mass, initial batch, initial charge is converted to polymer. Okay.
And that further leads to the further polymerization.
Yes. See, in the second step, within the cast mold, the residual monomer will undergo polymerization for further conversion to 40%, 50%, 60% to 100%. For example, you can test it in your laboratory. You buy a bottle of methyl methacrylate, okay, or styrene from the market, keep on the shelf, on the laboratory shelf. You do not have to do anything. Allow it to pass one summer when the temperature goes beyond 40 degree. Okay. After summer, you will find the entire monomer in the bottle has set to polymer, has been converted to polymer. Then you break the bottle, you will get a PMMA, your block, your cylindrical block from the bottle. If you come to my room, I will show you. I have such a block. These monomers are supplied along with some inhibitors. Hydroquinone. Hydroquinone is kept dissolved in the monomer, which acts as an inhibitor, which prevent the polymerization during storage, handling, transportation, etc. Still then, it is so sensitive for thermal polymerization. If it is not kept in the refrigerated condition, if it is not stored in the refrigerated condition, say styrene and methyl methacrylate, it undergoes polymerization in the bottle itself, even if there is inhibitor is present. But for polymer synthesis or manufacture, you have to remove that hydroquinone for getting proper polymerization kinetics, otherwise it will affect the polymerization kinetics. Okay. So, here you see in this slide you see there are various characteristics of this bulk polymerization. It provides minimum contamination of the polymer. As I said, it contains only polymer and residual catalyst or initiator. So, we can say you can get minimum contamination in the product. So, purest form of the polymer can be used for, can be available for, say, for medical purpose, biomedical engineering, where purity is a criteria. There you can use this bulk polymerized polymer. Simple equipment can provide this bulk polymer manufacture by bulk technique. Now, sometimes it is strongly exothermic for addition chain polymerization, whereas it is less exothermic for condensation chain polymerization. Now, if one goes to higher conversion, then it may give broad molecular weight distribution. Again, here is a science, underlying science in this telling broad molecular weight distribution at high conversion. What is that science? Now, as the growth occurs, the mass becomes more and more viscous. Okay. If it is addition chain polymerization or even if it is condensation chain polymerization, you can say that is a diffusion controlled polymerization. Diffusion controlled, I mean during polymer growth either by condensation polymerization or by addition chain polymerization. In both the cases, the reacting species should come closer. Think of addition chain polymerization, a growing polymer chain for its growth it needs monomer at its vicinity, okay. And at the point of termination either two such growing chain radicals come closer, okay, or one growing chain should come closer to, or one any other free radical in the say maybe from your initiator etcetera should come closer to their growing chain site for termination. Okay. So, that needs that is possible only if these growing chains species can diffuse within the mass. Now, that diffusion is restricted, get restricted by increase in viscosity, isn't it? Diffusion is restricted by increase in viscosity at higher conversions. Well, so, the other events of chain initiation and growth, those may not get proper access to growing to higher sizes. So, that gives a broad distribution of molecular sizes. So, actually the final polymer mass, in that final polymer mass the low molecular weight fractions might be formed at the later stages, because those low molecular weight chains may not be able to diffuse enough through the viscous mass, and that may get terminated. So, this actually this science should be understood, how that is the reason behind this broad molecular weight distribution at high conversion in a bulk technique. To understand that, you have to look at that picture of viscosity and diffusion of the free radicals. Okay. I said this problem of heat transfer. So, I showed this schematic of that polymerization reactor, where huge stirrer is used. Okay. So, with the progress of growth, viscosity becomes high and heat transfer becomes a problem, and that may lead to local hotspot generation, and there unwanted side reactions may occur, leading to polymer branch formation. Okay. Branching of polymer or unsaturation in the polymer etcetera, those are possible. Not only that, there may be possibility of various other isomeric structures formation within the polymer mass. Say, think of, I am telling you in one example, say butadiene. Butadiene, it can show various possibilities. You can get 1,4 linkage, you can get cis structure cis 1,4, you can get trans 1,4, you can get 1,2 or 3,4 linkage or pendant vinyl vinyl substituent from the same monomer. So, in one batch of polymerization, in one event of polymerization, you can have a polymer product which can be a mixture of 1,4-cis, 1,4-trans, as well as vinyl. Now, this composition you may say this may be maximum, say suppose it may be 90%, it may be 5%, it may be 5% or it may be 80% and say 15%, it may be 5% like this. So, overall you can say, looking at this composition, this will control the microstructure, polymer microstructure. That means, it can vary the polymer microstructure, and this polymer microstructure have influence on polymer properties during processing and service properties and processing properties. Okay. Their rheological characteristics will change, their mechanical properties will change, their thermal properties will change, their processing characteristics will change. You understand? So, as the viscosity increases, it causes problem of heat transfer, causes chances of runaway reaction. In order to avoid these things, direct cast polymerization, cast fabrication of polymer product is done. Okay. And it requires agitation, material transfer, separation and recycle in case of continuous phase polymerization. In case of continuous phase polymerization, better heat control may be available, and sometimes narrow molecular distribution can be possible. As you have seen here in this case, for high conversion broad molecular distribution, in order to avoid such broad molecular distribution, one can carry out continuous polymerization, continuous batch process, where since the conversion is low, in this case low conversion per pass, here molecular distribution will be narrower instead of broad, and in order to get such good narrow molecular distribution and good spectrum of properties, it needs agitation and it needs material transfer. I mean that there may be 70% unreacted monomer, that 70% unreacted monomer should be transferred, or before that it should be separated, purified and then transferred or recycled to the first reactor, so that there is no loss of monomer raw material. So, this is bulk polymerization. I have covered these problems and prospects of this bulk polymerization. Once again I repeat, it gives purest form of polymer, although control over the polymerization is less. So, in this case if somebody goes by batch polymerization, batch bulk technique or bulk polymerization by batch operation, if this batch size is small, there is a better control. So, here bigger batch size is not recommended and we can get a very good quality polymer. Thank you.